Yeah, hello and good evening. Anandi, are you able to hear me and are you able to see my screen? Hello? Hello? Are you able to see my screen? Am I audible? Can you just confirm, or if you cannot unmute, you can just give a thumbs up. Okay, so, or you can also write in the chat box. It's fine. Okay, I'll just start. So, right. So, in the last, just start the video. So in the last class, we were actually seeing a numerical problem on device characteristics, right? So the question was as follows. I'll just put on my headphones so that you are able to hear it better. So the question is, the gate voltage supply mentioned in question 1 is 0 volts and 20 volts. So we saw that 0 volts is the VEE or the negative bias supply, and 20 volts is the VCC or the positive bias supply. The Miller and threshold voltages of the device is 9.5 volts and 3 volts respectively. The gate input resistance of the device is 13 ohms. The device was blocking 625 volts and the on-state current is 20 amperes. Okay. So considering the first order approximate model of the gate transient, find the following. Okay. So Anand, if you are there, can you please confirm if I am audible and my screen is visible?
Yes, sir, you're audible, but your screen is not visible.
Okay, so just a second, I'll just share once more. Now is my screen visible?
Yes,
The
sir.
PPT visible?
Yes. Now it's visible.
Thanks. Okay, so I'll just go through it once again. So in the last class, we started off with some numerical problems, right? So the first problem that we solved was this. So for SiC MOSFET, the device capacitances are input capacitance 520 picofarad, output capacitance 39 picofarad, and reverse transfer capacitance 19 picofarad, right? So this is your CISS, COSS, and CRSS. So the question was determine the values for CGS, CDS, and CGT, right? So we solved this question by taking into account the parasitic capacitances that you find typically in a MOSFET, right? So you have the CGS between gate and source, you have the CGD between gate and drain, and you have CVS between drain and source. So CISS is the effective input capacitance with the output side shorted, right? It's like Thevenin's theorem, right? And the COSS is your effective output capacitance with the input side shorted. So CISS, if you short the output side, the output of a MOSFET, the output characteristic as we call, right? The output of a MOSFET is basically IDS versus VDS curve, right? So that's your output. So basically CISS is input capacitance with the output side shorted, means your drain and source or shorted means what is the effective capacitance. So you understand that if drain and source are shorted, it means drain and source are effectively at the same potential, right? So if they are at the same potential, we saw that that's why CISS is CGS parallel to CGD, right? Because drain and source are effectively at the same potential. So CISS is CGS plus CGD, right? And then COSS is the effective output capacitance, the input side shorted. So you short the gate and source, correct? That means that your effective capacitance looking from this side, right? Looking from COSS is going to be, let me turn on the point. Yeah. So COSS is going to be basically CDS in parallel with CGD, right? Because drain and source are effectively at the same point right now, and input is shorted. So I mean, gate and source are at the same point right now. So your input side is shorted. So COSS is basically CGD and CDS in parallel. And the reverse transfer capacitance is basically what? It is your connecting link between the input side and the output side. So, MOSFET is a voltage controlled current source, right? So, voltage is what? This is the gate source voltage. That's the controlling parameter. And of course, the output side is going to be your drain source, right? That's the current. Okay. So, reverse transfer capacitance is kind of the connecting link between the input and output, which is between the gate and drain, right? So the reverse transfer capacitance is directly CRSS or CGD. So once you know what is CGD, you can just solve a CISS equation and COSS equation to find out what is CGS and CDS, right? So that is what we did, and we found out that CGS was 552 picofarad and CDS is 20 picofarad. And one particular observation is that for all devices, mostly you will find the input capacitance much higher than the output capacitance, much higher than the reverse transfer capacitance. And since CRSS is the smallest and it is like very, very small in comparison to your CISS and COSS, you can safely tell that CGS is more than CDS, more than CGD, right? So this is an observation that you see for MOSFETs, correct? So any doubt in this question? So,
No, sir.
okay, thanks. If it is fine, we went on to the next numerical problem, right? So we were solving this numerical problem and we had to kind of stop in the middle due to lack of time. But anyway, it's a very good problem which makes you understand the device switching transients, right? Okay. So the gate voltage supplied to the device mentioned in question one. So the question one was based on the capacitances, right? Is 0 volts and 20 volts. So 0 volts corresponds to VEE or the negative bias voltage, and 20 volts corresponds to VCC or the positive bias voltage, correct? So the Miller and threshold voltages of the device is 9.5 volts and 3 volts respectively. So the Miller voltage is 9.5 and the threshold voltage or the voltage or the gate source voltage at which the device starts conducting, it's going to be 3 volts. The gate input resistance of the device is 13 ohms or the RG that we call it, right? It's 13 ohms. The device has blocking voltage of, the device was blocking 625 volts and the on-state current is 20 amperes. So your VDS is given and ID is given. Considering the first order approximate model of the gate transient, find the following, right? Okay. So one more thing is that since it is given here, the device was blocking 625 volts. So initially it was blocking 625 volts, means it was in the off state initially, right? The device was blocking 625 volts. So initially the device is in off state and then it turns on, the on state current is 20 amperes. Okay. So basically we are talking about which transient? We are talking about the turn on transient, right? You just gave the gate pulse to the device. So this was 0 volts and you gave 20 volts, right? So we are interested about what happens during this particular transition. We know that your voltage is going to kind of fall, correct? Your voltage is going to kind of fall and your current is going to increase, right? During this transition. Okay, but we will study in detail what is the mechanism that governs this, right? Or what is the governing equation that kind of describes this characteristic during the turn on characteristic. So if you understand the turn on characteristic, you can always extend it to turn off as well, right? So we will see how. Okay, so most of the parameters are given over here. We just listed them out. And then consider the first order approximate model of the gate transient. We saw that there can be parasitic inductances in the path, right? If you just take the gate source path, right? So if you just take the gate source path over here, VG, RG, and then CGS, which is the gate source capacitance. And due to the physical connections, we saw that there can be parasitic inductances of the order of few nanohenries. So if you include these inductances, what happens is you get an RLC network in the gate side, right? You can see my laser pointer. So that would make the system go into a second order kind of a response mode. And that's something that you will see practically. Okay. But just for the sake of solving this particular problem, they have told consider the first order approximate model, right? So if it is first order, obviously it means that you can neglect the inductances, parasitic inductances. That is, this is the source inductance and the gate inductance, right? So for this particular problem, we will not include any inductance in our computation. We'll just deal with basic RC networks. Okay. So that was your question, right? And the first problem was what is the peak gate current during turn on, right? So that was the first problem, right? So the device is turning on. At this instant, what is the peak gate current that is drawn? Okay, right. So to solve this problem, we saw, okay, so forgetting about this part, right? What is the peak gate current? Just take your simple gate side circuit, right? So you have a VG, and then you have RG, and then CGS. Correct. So during turn on, what happens? Your VG becomes equal to VCC, right? So your kind of VG travels from VEE to VCC, right? So your VG has been replaced with VCC, and then you have the RG, and then now we saw that the current that comes over here has two paths now. One can be through CGD and one can be through CGS, right? So during this particular transition, there is no change of drain source voltage. Your VDS is remains at VDC, right? So there is no dV by dt across your drain source, right? So in that scenario, and the device also doesn't conduct as well, right? So that is why what I will do is I will approximate CGD to be in parallel with CGS, right? So that is why we wrote that this is a simple RC circuit, right? Where the voltage across your gate source capacitance is called VGS, right? So this is VCC, that is the DC supply. Over here you have RG and then you have the capacitance. So it's a simple RC network connected to a DC voltage source. And we know that for a simple RC network that's connected to a DC voltage source, you have the VGS being governed as VCC into 1 minus e power minus t by tau, right? Where tau is your time constant, right? What is the time constant? Tau is equal to R into C, right? That is RG into CGS parallel to CGD or RG into CISS, right? So this is your tau. So VGS or the gate, so how is your gate source voltage going to increase? It's going to follow a profile something like this, VCC into 1 minus e power minus t by tau. Okay. So this was our condition, and of course you need to take the initial condition into account. In our case, the initial condition is 0 volts, right? Because in the question it has given us the gate voltage supply is 0 volts and 20 volts. We saw that if there was, let's say, minus 5 volts and it was not 0 volts, then you also have to include the initial condition in this particular equation. So your equation becomes VEE plus VCC into 1 minus e power minus t by tau. Okay. So um, this is your VGS, right? This is how the voltage across the capacitor is going to increase. And you of course know that um, beyond a long period of time, as time goes on increasing, VGS will get charged up towards VCC. And finally, VGS will be equal to VCC and the current would be zero, right? So initially the capacitor is kind of uncharged. So what would happen? There will be maximum current, and as the capacitor goes on getting charged, the current would go on decreasing, and finally when VGS becomes equal to VCC, the current would be zero, right? So this is what we saw, and to answer this particular question, we wrote that initially this capacitance is uncharged, right? Uncharged represent like it can be whatever is VEE. In our case, VEE was zero. So the initial current would be directly VCC by RG because the capacitor is uncharged, right? So I have just shorted it over here, right? So VCC by RG would be the peak current, and you know that as the capacitor goes on accumulating charge across it, what would happen is your gate current would go on decreasing, or the current through the circuit, right? That would go on decreasing and it would finally become almost close to zero when your VGS becomes charged to VCC, right? So that is what we saw. And the other case, if there is a initial voltage of minus 5 volts, right? It was not raising from 0 to 20. Let's say it was going from minus 5 to 20. In that case, the current would be what? The current would be VCC minus whatever is the initial voltage across the capacitor divided by RG. So which would be 20 minus of minus 5 by whatever is the RG, right? So this was how we computed the peak gate current, right? So peak gate current is basically just take the gate source circuit, the capacitor is initially uncharged or negatively charged. So that is the time when, or that is the instant at which there will be maximum gate current. And as time goes on increasing, your capacitor gets charged up more and more. So the current will go on reducing and finally it will reach zero, right? And one more thing we saw is that this is the peak gate current and it is drawn from where? This current is drawn from the supply, right? It is coming from VG, or practically when we do it, it is coming from the gate driver. So basically your gate driver IC that you put in, it has to be rated for a current which is more than this 1.54 amperes or whatever is the current, right? So your gate driver has to be rated for more current. So that is why you go to any gate driver data sheet, they will specify the current rating of the gate driver. Okay. So you have to make sure that your current gate driver satisfies the current rating. Okay. So till this point, is it fine? Like how the peak gate current was computed, just RC circuit. So
Yes, sir.
any doubt? Is it fine? Okay. Just to give you a perspective, I will try to open a commercial gate driver data sheet, and I think you can understand from there. UCC 21, let's say 750. I hope you are able to see my screen. So this is a TI data sheet. Okay, so a Texas Instruments gate driver data sheet. Okay, so in the last class we were saying about DSAT protection. So this gate driver has internal DSAT protection, and you see over here it says plus
Yes.
minus 10 amperes. So it means that this gate driver is rated to give plus minus 10 amperes peak. Okay, so this is what you should be looking for in the data sheet. Okay, fine. So one more thing is, in our case, can you just tell whether the gate driver is sinking current or sourcing current? Is it supplying current in our case? Or is it supplying current in our case, or is it so sinking current? Is it taking in current or giving current? You can understand that the direction of current is from VG, right? It is going out of VG. So VG is acting like a source, right? So it is actually sourcing current. The gate driver should be able to supply that much current, or it should source current. Okay. So in the gate driver data sheet, you will see there are two ratings. One is for source current and one is for sink current. Yeah. So it has up to plus minus 10 ampere peak source and sink current. So make sure that it can source this much amperes. Okay. Sometimes what can happen is the source and sink current can be different if you go to some other data sheet probably. So you make sure that according to your calculation, right, this is our sourcing current. Okay, this is the source current 1.54 ampere. The gate driver should supply. So make sure that your source current that's given in the data sheet satisfies 10 amperes. I mean, whatever is the uh, current rating that you compute. Okay.
Sir, what is
So
sync
if you're,
current?
sorry, what is?
What is that sync current? Sync current.
Yeah, so sink current is, you obviously understand the gate current would be negative, right? That is, the direction is opposite. So it means that I am taking away charge from the capacitor, correct? That is, I'm taking away charge from CGS and giving it back to the supply. So under which condition would it happen? Under which condition would I want to discharge CGS? During what period would I want to discharge CGS? So you understand I am dumping charges into your gate capacitance when I want to turn it on. I only when I dump charges, the voltage across EGS increases, it would go beyond threshold and the device starts conducting, right? So this is during turn on period. So you imagine what would happen during turn off period. I want to turn it off, right? I want to make sure that the gate source voltage goes below threshold voltage so that the device turns off, right? In that scenario, what do I need to do? I need to make sure that the voltage across your gate source capacitor goes below threshold voltage, right? So I need to remove charge from the gate, right? So that is when your gate current becomes negative. You understand, right? So it would be during the turn off period that you will be sinking current into the source. I mean, you will be sinking current into VG. So the direction would be opposite. Do you understand? I would remove current
Yes,
from
sir. The current
CGS.
is reversing to the source.
Correct. Correct. So that would happen during turn off. So what people do is like they have different values of RG during turn on and turn off. Okay. So you have to compute what is IG peak during turn on and you have to compute what is IG peak during turn off. Thus the RG value will change. And based on that, your IG peak will change and your gate driver should be rated to sink that much current. So both of these aspects you need to see. Okay. We will see why, but you will see that there is generally there will be an RG during the on time and RG during the off time, right? So generally people keep the RG during off time lesser than on time. Okay, we will see why. But anyway, so if your RG is lesser, you know that IG could be higher, right? So for RG of 13 ohms, IG peak is this much. If let's say RG is 5 ohms or something, then IG peak would be much, much higher. Okay. So you need to make sure your gate driver can sink that much current. Generally, people keep the off gate resistance lesser than on gate resistance. You will see why later, but you understand what is sink current and source current, right? Just during turn on and turn off, it should be able to source that much current and sink that much current. Okay, is this fine? Yeah, so
Yes, sir.
okay, so are you able to follow this or like are you computing, making any notes or something or just seeing it?
Yeah, I'm taking notes on it.
Okay, great. Because numerical problems, it's better to take notes now. Like, it's better to revisit later. Okay. Okay, so we will just move ahead to the next question, right? Mm. So yeah, so one more aspect we saw was that this was generally for silicon carbide devices, right? You use gate voltages between 0 to 20 volts. For IGBTs, you use between 0 to 20 volts. Okay. So I just write it down over here. So just it's an extra piece of information. So for IGBT, you will use 0 to 20 volts. For SiC MOSFET, right, you will use 0 or -5 to 20 or plus 15 volts, and for GAN it is between uh, minus 3 to plus 6 volts, or it's even between 0 to plus 5 or plus 6. Okay, so can you tell for the same gate resistance, right? I'm using same gate resistance in all three cases for IGBT, SiC, and GAN. So in which case my peak gate current requirement would be lower? So IG peak, in which case would it be lower? So same gate resistance for IGBT, SiC, and gallium nitride. Okay. So IGP could be lower for which case? Can you tell?
Again,
Yeah, right. Because the VCC minus VEE difference, it is the least for GAN, right? We saw that IG peak is basically VC by V by RG, right? That is the voltage difference divided by RG. So if your voltage difference is lower, that is over here, it's only plus 6 minus 3, it's maximum 9 volts, right? Or even less than that. So obviously, since your voltage is lesser, the current requirement is also lesser for the same gate resistance. Okay, yeah, so this is what we solved that day. Okay, so next question was, what is the current rise time, right? So over here, I have drawn the current increase. This is your I. So what time does it take for the current to rise, and what time does it take for the voltage to fall? This is something we started off in the last class, but we had to kind of discontinue in the middle. So the question is, what is the current rise time and di by dt during turn on? So if you know what is the current rise time, di by dt is simply I by t, right? So that is not an issue. But we have to find out what is the current rise time, right? So, okay. So towards this, we made some progress, correct? So let me go back to the circuit that we were referring over here, right? Um, just hang on a second. I will just turn on my fan and come. It's becoming hot. Yeah. Okay. So we left off from over here, right? So the first instant was, or the first interval was during the period when you have just given the supply source, right? So we saw that your VGS was initially at VGE. In our case, VGE is 0, right? So once you give positive VG, right, that is, you make the VG go from 0 to 20, right? So I think I did not draw that, so I'll just draw it over here. So you made your VG go at this particular instant, your VG went from 0 to 20 directly. Correct? Your VG went from 0 to 20. It was 0 and to 20. And we were seeing how the dynamics would look like, how the gate source, drain source, and drain source voltage and the current would look like. Correct? So we saw that initially during till the instant 1, right, or interval 1 as we can call it now. Correct? So, so we saw that from VEE, obviously your gate source voltage starts increasing. Why? Now there will be a gate current which will flow through the circuit, right? There will be a gate current which will flow through the circuit. As the gate current flows, what will happen is more and more charge is dumped into CGS, correct? More and more charge will be dumped into CGS, and hence the gate source voltage will slowly increase. How would the gate source voltage increase? It would increase based on this particular relation, right? It's just an RC network. VCC into 1 minus e power minus t by tau. And so this is how the gate source voltage is expected to increase. But for simplicity, we told that let's assume this particular region is kind of linear, right? That is why I have marked it in red over here. We told that let's assume it is linear for now. So gate source voltage is increasing linearly during this particular region. Okay, so gate source voltage increases linearly, and yeah, so your gate source voltage slowly increases. It is still below the threshold voltage, right? It is still below the threshold voltage, so it will increase until threshold voltage. Let's call that interval 1. Okay, and since during this entire interval your gate source voltage is less than the threshold voltage, obviously the device is turned off, right? The device is turned off, so there is no drain source current, right? No drain, so it cannot carry any current, and it is blocking the entire DC bus voltage, right? It is blocking the entire DC bus voltage. So this is something we saw. Okay, so drain source voltage would be equal to DC bus voltage. So this was our interval 1. And we also saw, okay, so after this, we went to the next region, but meanwhile, we also saw what are the regions of operation for a MOSFET, right? So we know that MOSFET can operate in 3 particular regions. One is the cutoff region, saturation region, and ohmic or the linear region. This can be observed from the device output characteristic, that is ID versus VDS. So cutoff region is pretty simple. You know that the device is totally turned off, so the current it carries is going to be 0, and VDS would be equal to VDC, right? Till interval 1. I mean till instant 1, right? And why is it so? Because your gate source voltage is less than the threshold voltage, so it cannot carry any current, obviously. So this is pretty clear, right? So you understand that this interval 1, entire period of interval 1 is marked by cutoff region. The device is in cutoff region, so it doesn't matter, right? Okay. So I forgot to mention one particular thing to you, that this period, right? That is the period from mm, the period from t equal to 0 to t equal to 1, right? This particular period, that is the instant at which your VG became 20 volts, that is the instant at which you gave the gate voltage, and to the instant at which, till the instant at which the gate source voltage becomes equal to threshold voltage, right? This is called a turn on delay time, TD on. Okay, this is called turn on delay time. That is, this is the delay taken by the gate source, gate side circuit because of RC, right? So obviously this delay is introduced by the RC network in the gate side, right? So this is called turn on delay time. So you gave the gate pulse, right? That is, you gave VG of 20 volts at a particular instant, but from there it took this much time for the gate source voltage to actually rise till the threshold voltage, because you know that the device starts conducting only after it hits threshold voltage, right? So this period in between, it is called the turn on delay time. Okay, so this is called turn on delay time, right? And it's throughout the turn on delay time the device is in cutoff region. Okay, fine. So with next we went on to the next region, that is between interval instant 1 to instant 2, right? So what happened at instant 1, your device gate source voltage has become equal to threshold voltage, and as VGS increases, your VGS will increase beyond threshold voltage, right? So you know that if VGS is more than V threshold, the device is going to turn on, right? After instant 1, the device is going to turn on, right? Okay. So in turn on condition, there are two regions. One is the saturation region and one is the ohmic region, correct? So it's essential for us to actually quantify or qualify under which region the device is operating, right? So In both the cases, that is in both saturation and ohmic region, the device is turned on and VGS is more than V threshold. But what defines these two regions is that what is the VDS across the device, or what is the voltage that the device is blocking, right? If your VDS is more than VGS minus V threshold, VGS minus V threshold is, as VGS increases, this difference will also change, right? But if your VDS is more than VGS minus V threshold, then it is in saturation region, right? And it behaves like a voltage controlled current source. This is something we saw in the last class as well. It behaves like a voltage controlled current source where the controlling voltage is VGS, voltage controlled, right? So the controlling voltage is VGS and it's a current source. So current source is basically the channel current or the drain source current. Okay. So your I channel would be GM, that is your transconductance, GM into VGS minus VTH. Remember that at a particular value of VGS, your I channel would be constant. Okay. So your I channel would be constant at a particular value of ID or at a particular value of VGS. So it means that the device is in saturation region. Under saturation region, your VDS would be more than VGS minus V threshold, and we saw that the device acts like a voltage controlled current source, and your channel current is GM into VGS minus VTH. Okay. The other region is your ohmic region or the linear region as we call it. So your VGS is again more than V threshold, but the defining parameter is that VDS, that is the drain source voltage across the device, is very small. Drain source drop would be less than VGS minus V threshold. If this is satisfied, right, then you can tell that the device is an ohmic region and you may approximate the channel to be a resistance, RDS, right? You can approximate the channel to be a resistance, RDS, right? And we saw that this RDS is a function of the junction temperature, right? Your transconductance is also a function of the junction temperature, right? This is something we saw later on. Okay, so now, yeah, so I'll just take you guys to a, let's say, a commercial device data sheet and just show, right? So, so let's go to a manufacturer. So Infineon SIC MOSFET, correct? So Infineon is a well-known company that manufactures devices and modules, okay, and even other ICs as well. So yeah, so let's select a product. Um, it's a long time, right? So yeah, so let me go to um, let's take this particular MOSFET, right? It's slated for 650 volts VDS. Okay. So we go over here and this is the package of the MOSFET and let's go to data sheet. So just for your information, this particular value TO247, it is the name of this package, right? This is the package that the MOSFET comes in. And -3 indicates that there are three legs, that is drain, source and gate. Additionally, there can also be a Kelvin source. We saw that I think in the starting, but anyway, this has only three legs. So TO247 indicates package. Okay, there are other packages as well. So anyway, that is not the idea of this, but Yeah. So this is your drain source characteristic, right? Output characteristic. So you see that initially you have the cutoff region, and then you have the linear region over here, right? That is, as you can see my mouse, these are the linear regions, and later on the current kind of starts to get saturated. So that is your saturation region at higher values of VDS. Okay, fine. So let's go back over here. So now can you tell, once the MOSFET turns on, that is once your VGS exceeds your threshold voltage, it is in which region? Is the MOSFET is in linear ohmic region or in saturation region, and why?
It is in saturation region.
Correct. Why? Because it's blocking VDC, right? It's still blocking VDC. Okay. So we assumed that for practical purposes, let's assume that the VGS increases linear, right? Your VGS increases linear, and in that case, as your VGS increases linearly, IDS, right? That's the channel current, GM into VGS minus V threshold, that would also increase linearly. Okay, so we assumed that this particular increase is linear. So if this is linear, then your drain source current increase or your channel current increase is also linear, because channel current is directly proportional to your VGS. Okay, for a fixed value of GM and a fixed value of V threshold. Okay, yeah. So one more thing that I wanted to show. So, mhm. Yeah, so you can see over here that we approximated basically ohmic region. The device is like a resistance RDS, right? And this, it turns out that RDS is a function of the temperature. If the temperature is higher, the resistance is also higher. It has a positive temperature coefficient. Okay, as temperature increases, RDS increases. So if you operate at higher and higher temperature, the RDS would be more and more. So therefore, your conduction loss, I square R loss across the MOSFET is going to be higher. Okay, so your RDS, right? You can see over here, this is drain source on resistance versus TJ, junction temperature. As junction temperature increases, your RDS also increases. Okay, and I think, hmm, okay, so I think this is enough for now. Okay, so okay, so coming back, so your gate source volt, oh, your your gate source voltage increases linearly, and hence your current also increases linearly. And during this period, we saw that there is no fall in VDS, right? Because it's like a current source, voltage controlled current source, right? And we also saw that why does the voltage fall? We saw this very elaborately in the last class, right? That is, let's take the double pulse test setup that we have been seeing so far, and let's assume that S2 is turning on, right? The device S2 is turning on, the lower device is turning on. Initially, what would happen? Initially, the device was off, therefore the entire inductor current, right? The entire inductor current was freewheeling through the anti-parallel diode of the top device S1, right? It was going through the anti-parallel diode of S1, right? And since this device is in conduction, so you know that the voltage would be entirely appearing across S2, right? You can just see over here that the voltage would be entirely appearing across S2. That was the initial condition. Initially, the entire current is freewheeling through the antiparallel diode of S1, right? So until the instant 1, during the turn on delay time, right? So until that point, your inductor current freewheels through the antiparallel diode of S1. Okay, then we saw that we turned on S2 by making sure that the gate source voltage increases beyond the threshold voltage. So as VGS increases, since this is like voltage controlled current source, right? I don't know whether I drew it or not. Okay. So since this is like voltage controlled current source, you can approximate the channel as a current source. So slowly what would happen? The current through S2 would slowly increase, right? So since your inductor current is fixed, right? Your inductor current is like a constant current source, 20 amperes. So 20 amperes is flowing over here. Now it splits into some current through S2 and some current through the antiparallel diode of S1. Initially, the entire current was flowing through antiparallel diode of S1. So that is 20 plus 0 as I have written it, right? Then what happens as S2 turned on, as S2 started behaving like a controlled current source, as VGS increases, the current through this device increases. So the current gets split, the total 20 ampere gets split into some current through S2 and remaining current through the anti-parallel diode of S1. Okay. Now what happened? Your S2 gate source voltage went on increasing. Your VGS goes on increasing. Therefore, your channel current goes on increasing. At some point, right? So what happens? More and more current would be flowing through S2 as VGS increases. More and more current would be flowing through S2. And at some point, what will happen is entire current starts flowing through S2, right? Entire 20 ampere current will start flowing through S2 and there is no necessity of the antiparallel diode of S1. Entire current will start flowing through S2. It has to flow, right? Because there is a current source, right? So there is no splitting of current once the current source value becomes equal to the actual 20 amperes. Okay. So what happened initially, we started with antiparallel diode of S1, then slowly the current through S2 increased, slowly current through the antiparallel diode decreased, and what happened was finally the entire current is being carried by the channel of S2, which is so far in the saturation region. Okay. And why is it that the voltage across S1 doesn't split? We saw that the current is splitting, right? The current is splitting into this and this. Why doesn't the voltage change? The reason was that until the diode conducts, right? You take normal diode conduction. Diode can conduct only when anode voltage is more than cathode voltage. Simple, correct? If there is a positive voltage from cathode to anode, the diode cannot conduct. Okay. So So you know that if there is, let's say, a voltage like this, the diode cannot conduct, right? Cannot conduct, correct? So this is if there is positive voltage like this, if there is a voltage across the diode, something like this, the diode cannot conduct, right? That is why until the diode carries some current, until this point, right? Until the diode carries current, so until the diode carries current, the voltage across S1 cannot be positive. So the entire voltage will be blocked only by S2. Okay. It's a current source. So current source can block voltage. It's not an issue. So the voltage across S2 will be VDC. That is why we saw that the voltage is still VDC, right? The voltage is VDC over here. Why? Until the entire current is being carried by S2 alone, right? Until any current is being carried by the antiparallel diode of S1, the voltage cannot change because a diode can carry current only if the voltage across anode to cathode is positive. Cathode to anode cannot be positive. Okay, so S1 cannot block any voltage until the antiparallel diode conducts. So this is a very vital information. Okay, fine. So another thing, so this particular period is known as the current rise time. That is the time taken for the channel current to increase from 0 to the whatever is the full load current. In our case, 20 amperes, or I think, yeah, 20 amperes. Right? This is your current rise time. And in this case, the voltage remains VDC. Okay. So finally, what happened at instant 2, right? At instant 2, your drain source current reached the load current, and your VGS at this particular instant, right? VGS was increasing all along. At the particular instant when the device starts carrying the entire full load current, right? That particular gate voltage is called V Miller. Okay, this particular gate voltage is known as V Miller. Okay. Okay, so what happened during the current rise time? Your gate source voltage increased from threshold voltage at which the current was zero, and it increased from V threshold to V Miller, right? At which the current becomes equal to the full load current. Okay, so this is your current rise interval. So first we have the turn on delay time, wherein the gate source voltage is less than V threshold. So the gate source voltage rises from 0 or VE to V threshold. The current on all is 0. And then you have the second interval, that is your current rise time, wherein the device is in saturation region. The current increases based on Gm into VGS minus VTH. As VGS increases, your drain source current increases. So VGS will go on increasing from V threshold to V Miller. V Miller corresponds to the gate source voltage at which your device starts carrying the full load current. Okay, and the drain source voltage cannot change. Why? Because there is a diode over here, anti-parallel diode. As long as this diode is in conduction, the voltage cannot change. Simple. Okay, fine. And one more salient feature of this particular interval is that see, there is current which is rising from 0 to IL, right? 0 to 30 amperes. The voltage is VDC. Okay, voltage across the device is VDC. So you see that current is also non-zero over here. Current is increasing and the voltage is very high. Voltage across the device is very high. So what is the power across the device? The instantaneous power loss across the device. The power across the device would be quite high, right? Because V into I is the power. I is also very high. V is also very high. So your power loss would be enormous during this interval, right? That is during this TR, if you calculate the power, right? Just do V into I, you will get very high values of power during this interval. That is why I want to lessen the time for which this power loss is happening. Correct? I want to lessen the time for which this power loss is going to happen. That is why people want to keep lesser and lesser TR always. Okay. So do you understand till this point? I think so. Is this fine? This was a recapitulation of what we discussed in the last week. Any doubts so
Yes, sir.
far?
Yes, sir.
Okay. Anandi, is it fine?
Yes, sir. Yes.
Okay. Okay. So as I was telling, this particular region should be as small as possible, and that is why we want to have lesser and lesser rise time. So that is so TR should be less. So how do I make sure that TR is lesser, right? So one particular way of making sure your TR is lesser is making sure that your VGS increases quickly, right? Instead of VGS increasing like this, let's say my VGS increases like this, right? So then my current would reach IL at a quicker time. Okay, so the time is lesser, right? So this is one particular way. I want to make sure that VGS increases faster. So how do I make sure VGS increases faster? It is a simple RC circuit, right? We saw this in RC circuit. Okay. Yeah. So this is a simple RC circuit, right? So if I can reduce my RG, capacitor would be charged faster and faster. So people try to reduce RG. If I reduce the gate resistance, the capacitor would be charged faster. So if my VGS increases faster, then my IDS would be faster, your TR would be lesser, rise time would be lesser. Okay. That is why people reduce RG, but we saw that if I reduce RG, your peak gate current, right? RG is lesser means your peak gate current would be higher, right? If I make RG, let's say instead of 13 ohms, I make it 5 ohms, right? If RG is 5 ohms, then 20 by 5 is 4 ampere, which is quite high. Okay, so peak gate current requirement increases more and more. There are other issues as well, but this is one particular issue. Okay, so people want to reduce RG so that the time for which this loss happens is reduced, but you have some constraints. Okay. Okay. So this was the second interval. Okay. Fine. So before we move ahead to the next interval, I will just okay, probably will yeah, I will just solve this particular problem. Okay. So the problem was to find out the current rise time, right? So so I'll just take a new slide over here. So let's solve it using nodal analysis or using our basic principles. Okay. So I'll just okay. So right. So we saw that let's say this is the t equal to 0 interval. Okay. Okay. So your VGS was initially at VE, and then at this point, okay, so let me draw it in another color. Okay, so your VG was initially VE, and at this point, I gave a VG which went from 0 to 20 volts. Okay, and we wanted to see how VGS would look like, correct? So VGS was 0, and then we saw that it slowly increased till V threshold. Okay, so this was our VGS. So of course, since it is less than V threshold, my drain source current are going to be 0. So drain source current is 0, and your drain source voltage is going to be VDC. So this is V threshold, and this is 0, and this is going to be VDC. Okay, so what would happen to the gate current, right? IG. This is very important if we have to solve this problem. Okay, so what would happen to the gate current? You imagine it's just an RC network. So till this point, the gate current was 0. At this point, I made VGS go from 0 to 20 volts. VGS went from 0 to 20 volts. Correct. So VGS went from 0 to 20 volts. So what happened was, we know that peak gate current would happen here, right? So this is the instant at which the capacitor is totally uncharged and you have a VGS that is happening, right? That is, you have VG going from 0 to 20. Okay. So there will be a peak gate current at this particular instant. Okay. So let me call this as IG peak. Okay, IG peak, this is simply V by R. And you know that if there is, let's say, a capacitance, right? It's an RC circuit once again. So as the voltage increases, the current decreases, right? So you would know that as your voltage increases like this in an RC circuit, the current would go on decreasing. The current would go on decreasing like this. So do you understand this? You agree with this, right? As when the capacitor is initially uncharged, there will be peak gate current, and as the capacitor goes on charging, the current would go on decreasing, right? Yeah. So I think this is fine. So if this is fine, then is this fine? Like the capacitor current or the RC circuit current will go on decreasing as the capacitor charges and charges. So you can tell that there will be, this is the peak current. Okay. So this is the peak current, IG peak, and slowly the current goes on decreasing. So similarly, right? Similarly, IG peak occurs at this particular instant, and then what happens is your IG peak would decrease. Since we have assumed a linear increase in gate source voltage, I will assume a linear decrease in the gate source current. Okay. So I have assumed a linear decrease, right? So let me call this one as I1. Let me call this one as I1. Okay. So as during the turn on delay time, right? So during the turn on delay time, as your gate source voltage increases from VE towards V threshold, your gate current comes down from IG peak to a value I1. We don't know what is the value I1. Okay. Or we can write as well. So let's go back to the circuit once again. Um, right. So, okay, so let me go over. Yeah. So the circuit is what? Circuit is basically this is VGS and this is VCC. This is RG. Okay. This is CISS. Okay. So can you tell uh, at VGS is equal to 0 volts? We know that your IG is going to be VCC minus 0 by RG or VCC by minus VEE by RG, right? At VGS equal to V threshold, right? This is the point, right? This is the point. I1 is the point at which VGS is equal to V threshold, right? VGS is equal to V threshold. I1 is the point at which VGS is equal to V threshold. So your IG during that point is going to be how much? VCC minus V threshold by RG. This is what we called as I1. Do you agree with this? Is this fine? What is I1? I1 is basically VCC minus V threshold by RG. This
Yes, sir.
voltage by RG. Simple, right? So this is our I1. I1 is known because they have given the threshold voltage of the device. I know what is I1. Okay. So then what happened? Beyond that, we saw. Okay, sorry. We saw that current was increasing. So current increased from 0 the device was in saturation region, so the current increased from 0 towards IL, right? And finally it hit what is IL. Okay, so let's say this is the point at which we hit IL. Okay, and this is your current rise time as we call it. So yeah, and we also saw that when the current is increasing, since the antiparallel diode is conducting, your VDS cannot change. The voltage across the device will not change during this entire interval, and your gate source voltage continues to increase linearly. This is an assumption we made. So gate source voltage continues to increase linearly, right? Gate source voltage continues to increase linearly. Okay. So since gate source voltage increases linearly, right, I can assume that the gate current falls linearly, right? Gate source voltage continues to increase, so gate current continues to fall. So I'll just make one change over here, or just for making sure our diagram is good. So, so let's let it fall like this so that I get enough space. So this was our I1. So I1, right? And gate current continues to fall linearly. So it falls like this, and let's call this as I2, right? And oh, okay. So this is our current rise time period. So current rise period. Okay. So this was TD on, turn on delay time, and this was the current rise interval TR. Okay, fine. So this is I2, and we told that the voltage, gate source voltage at which your the device starts carrying the entire full load current, right? So this is your IL, right? So this is your IL, full load current. The gate source voltage at which the device starts carrying your full load current is known as Miller voltage. Okay, this is also given in the problem. So V Miller. Okay. Okay. So now you understand what is I2, right? So I2 would be directly at VGS is equal to V Miller. Your IG is going to be VCC minus V Miller divided by RG. This is your I2. Okay. Again, simple, right? Just it's an RC network. Okay. Fine. So this is your I1 and I2. I1 and I2 are determined so far. Correct? So till this point, is it fine? How we drew the gate current? Just assume linear increase in gate source voltage. So gate current falls linearly from IC peak. We computed what is I1, I2 based on simple RC network. Okay, fine. So one way of writing IG was based on these equations. Okay, that is simple voltage drop across RG. This is in terms of RG, right? So can I write what is the current in terms of CISS? Can you tell? So I have written equation in terms of
RG. Can we write in terms of CISS? Are you understanding the question? Can I write in terms of CISS what is the current? So just look at CISS. What is the current? Simple. You take a capacitor, okay? There is a voltage across it, V of t. There is a current, I of t. So what is the equation that would give me I of t in terms of the capacitance and all? In time domain, not in frequency domain, in time domain. Can you tell? It's very simple, like, huh?
C into dV by dt. The first thing.
So C into dV of t by dt, correct. Can you apply the same thing over here and tell me what would be Ig? In this particular thing? Just same thing. So I of t C dV by dt, correct. Same thing, just substitute over here. So what would be Ig of t? What is the capacitance? CISS, right?
CISS.
C into what is the voltage across the capacitor? D VGS by dt. Do you understand? Are you able
Yes.
to follow this? Simple,
Yes.
right? D VGS by dt. Okay, so simple. We have written gate current in terms of RG. We have written gate current in terms of CISS. Very simple equations, right? Okay. So now can you tell me during this particular so dVGS by dt means what? Change in the gate source voltage, right? So let's write over here um, during TD on, right? So just a second. Mm, okay. Yeah, yeah. So during TD on, right? You're during TD on, your VGS changes from what to what during TD on? It changes from
VDS not
VEE
changing.
to
VGS.
no VGS. VGS changes from VGS changes from VGS changes
Zero
from what
to
to what?
threshold.
Correct. So VEE to V threshold. Okay. So in that period, what is IG? IG is going to be CISS into dVGS by dt. So what is the change in VGS? V threshold minus VEE divided by the time period TD on. Do you follow this? C dV by dt during interval 1, during TD on. Do you follow?
Yes.
Okay, good. So this is during the first interval. Oh, what happened, man? Okay, so this is during the first interval. So this is your capacitor domain equation. Okay, and during TR, right? During TR, VGS changes from what to what during TR?
VTH to VM.
Correct. VTH to VM. So your IG can be written as CISS into Vm minus V threshold divided by Tr, correct? Right? Okay. So you observe one thing that over here the gate current is changing, right? It's changing linearly. So during interval 1, it fell from Ig peak to I1. During interval 2, the gate current fell from I1 to I2. But this capacitor domain equation is actually giving me a fixed current, C dV by dt. So it is giving me a fixed current, right? So basically you understand that since we have assumed that the gate source voltage and all is linear, right? It gives you the average current Ig. Okay, so the average current Ig during this interval is this. Average current Ig during TR is this. So you can assume that the average, let me draw using a different color. The average would be something like, uh, so during the first interval, the average was somewhere here. During the second interval, the average was somewhere here. Are you following this? This is just the average current. The average current is this. Okay. Are you understanding?
Yes, sir.
Okay. So now from this equation, we can get what is TD on, what is TR. Okay. I will just take a different slide. I hope you're understanding, right? It's just average. It is giving me a single value during this entire region. During TD on, it is giving me a single value. During TR, CISS into dV by dt, it's a single value, right? Since you assume that voltage is increasing linearly, C dV by dt would be constant. Okay, because dV by dt is constant. Okay, that is why it's giving me the average value of gate current during interval TD on, average value of gate current during the interval TR. Okay. Fine. So we have to equate these equations with these equations. Okay. Fine. So that will directly give us what is TD on and TR. So let me take a new slide. Okay. So I'll just draw what is VGS and IG alone. From there we can go ahead. Okay. So your IG was IG peak, and then it slowly falls to I1, and it continues falling till I2. It continues falling till I2. Okay. And what about your VGS? Your VGS was initially at VEE. It slowly started increasing. It hit V threshold, and beyond that, it continued increasing linearly. Right? So let me mark these. Correct. And IG peak, I1. This was I2, right? And okay, TD on TR, right? And we also saw what was the average gate current. So the average gate current was somewhere over here, and then somewhere over here, right? So this is your average gate current during the interval TD on and TR. So this was VE, this was V threshold, this was V Miller. Okay. So let's take interval 1. Okay. Let's take interval 1. That is, this is interval 1 and this is interval 2. So in interval 1, right? So in interval 1, just a second. Okay. It will allow me to copy the slide the next slide as well. Okay. So in interval 1, right? That is during TD on. We saw two values for gate currents. So one is IG peak is basically VCC minus VEE divided by RG, right? I1 is VCC minus gate voltage is V threshold divided by RG. And again, we saw that the IG average during this interval is going to be simply C dV by dt, CISS, into the voltage changes from VEE to V threshold linearly. So VEE to V threshold is basically V threshold minus VE divided by the time is TD on, right? So these are the governing equations. So this is a single value of current, right? That is IG average is a single value of current, but the gate current actually changes from IG peak to I1. Okay, IG peak to I1. So what you can do is find out the average between IG peak and I1 and then equate it with IG average. Are you understanding what I'm telling? Is this fine? Find out the average between IG peak to I1, right? That indicates the average gate current during that interval, and then you can equate it with C dV by dt. Okay. Okay. So the average is what? Average IG is basically IG peak plus I1 by 2, right? So this is 2 VCC minus V plus V threshold divided by RG, right? So equate this with this equation. Therefore, you will get what is the turn on delay time. Okay, fine. Do you agree to this point? Similarly, during interval 2, I know what is IG average, C dV by dt. I know what is I1 and I2. Find out the average of I1 and I2. That will give you this line. Then you can equate them. Okay. Do you understand this, Anandi and Selva Kumar sir?
Yes, sir.
Right? It's simple only, right? So it's not that big a deal. Okay. So I'll just copy this. How do I copy? So during interval 2, right? So that is during the rise time. What you know is basically I1. I1 is what? VCC minus the gate voltage is V threshold divided by RG. I2 is VCC minus what is the gate voltage? V Miller, right? VCC minus V Miller divided by RG. And what is IG in terms of CISS? CISS into dV by dt. Voltage is changing from V threshold to V Miller. Okay. So Vm minus V threshold divided by Rg. Okay. So now find out the average gate current during this interval between I1 to I2. Okay. Ig average is what? I1 plus I2 divided by 2, right? So 2 VCC minus V threshold plus Vm divided by Rg. Equate these two. We want this answer only, right? So equate these two. Oh, sorry, I made a mistake. So this would be basically
TR.
TR. Correct. C dV by dt. Okay. So from here you can write directly what is TR, right? Just equate both of these, you will write, right? So what would be TR? CISS into Vm minus Vth into Rg divided by 2 VCC minus V threshold plus Vm. Is it correct? Oh, sorry. I think I missed a factor, right? I1 plus I2 by 2. So 2 Rg. Right? So 2 Rg into 2 Rg. Do you agree with this? Is this fine? Okay, just find out Ij average and then you equate it.
Yes, sir.
Okay, dimensionally it will satisfy. Voltage and voltage are cancelling, then you end up with only RC. RC is time constant tau, so it dimensionally satisfies. Okay, yeah, dimensionally it is satisfying. It comes out to be around RC. Okay, so now in this we will substitute our parameters. Okay, so let me take a new slide once again. So let's copy this or yeah. So in our case, CISS was how much? CISS CISS is 571 pico, correct? CISS is 571 pico. And VM is 3 volts. Oh, sorry, V threshold is 3 volts. VM is 9 volts. I forgot. 9.5 volts. 9.5 volts. RG is 13 ohms. VCC is 20 volts. Can you find out what is TR? Just substitute these values. You will get what is TR in some. Tell me in nanoseconds if you compute. 571 into 6.5 into 10 divided by series 40. Yeah, I'm getting somewhere around 3.5 nanoseconds. Are you getting this? Is this fine? Any doubts? Huh? Mm. Okay. Yeah, I think it is correct. So TR is RG into CGS into PSEISS into V minus V threshold divided by 2. Yeah, this is correct. The formula is correct. So are you getting this? Are you getting somewhere around this? What is TI? 3.5 nanoseconds. Is it fine? Okay. So did you understand the entire process? How we define TR? How we designed for TR? Hmm.
Yes.
Okay. Yeah. So this indicates this particular interval. Okay. TR, current rise time. So current rises from 0 to 30 amperes in 3.5 nanoseconds. Okay. For this particular problem. Hmm. So if your CISS is larger, right? If your CISS is larger, your TR also increases. Rise time increases if your CISS is larger, obviously. If your RJ is larger, TR increases, rise time increases. So as CISS or RG increases, your rise time also increases. Okay, that is why people go for wide band gap devices like SIC and GAN. Okay, for SIC and GAN, you will see that CISS is much lower. So the TR is also lower. Okay. So CISS is lower. So your TR is lower. Therefore, there will be lesser overlap between the voltage and current. We were talking about this overlap, right? There will be lesser overlap between the voltage and current during this particular interval. So the loss will occur for lesser amount of time. The heating up of the device will be lesser. Okay. So is it understood, Anandi and Selvakumar sir? How we compute what is TR?
Yes, sir.
Okay, so then we will go on to the next interval then. Fine. So uh, the next interval is to understand what happens during the once your drain current has increased to IL, right? Then what happens? So one thing we saw was that till yeah, so till the antipenal diode is conducting, right? And after the antipenal diode stops conducting, the diode current falls to zero. Correct? The diode current falls to zero, but unfortunately, the diode also exhibits a reverse recovery. Okay, so there will be a reverse recovery through the diode, right? There will be a reverse recovery through the diode. So there is a negative current through the diode, right? That negative current will complete its path through the other device, S2. Okay, so this under dip in the current through S1 will be reflected as overshoot in the current of S2. That is why we saw something like this reverse recovery current. Okay, the reverse recovery current of the complementary device will appear in the other device. Okay. So one was the reverse recovery aspect, right? I think we saw this also. Okay. The other one was, see, okay. So now the diode has stopped conducting. Okay. No current through this diode, no current through this diode. Entire current is being carried by the other device. So after this happens, after the diode current becomes zero, your voltage will start to change, right? So since the device S2 started to conduct and S1 stopped conducting, now the voltage should transfer from S2 to S1. So VDC will be blocked by S1 and S2 will conduct with almost very negligible voltage. The voltage would be just V equal to IR drop. Okay. So anyway, one more thing is the device was in saturation region till now, right? Because the voltage was very high, so the device was in saturation region till this point, right? Device was in saturation region till this point. Okay. So then what happens is slowly the voltage starts to change. If you tell that the voltage starts to change, basically it is the capacitance, right? We told that there is the output capacitance COSS. What is COSS? COSS is basically CGD plus CDS, right? Or CDS in parallel with CGD. Okay. So COSS, right? So what happens if the voltage changes? It means that voltage across a capacitor is changing. If you tell that the device is blocking 400 volts, it means that COSS is charged to 400 volts. Okay, that is COSS is blocking 400 volts. And if you tell that the device is turning on, it means that voltage across the device falls. What do you mean by telling that voltage across the device falls? It means that the COSS is discharging, right? So that is what we established convention that if it is charging, you're pushing current or charge into the COSS, right? This is the polarity of the capacitor. If you tell current flows like this from top to bottom, the capacitor voltage increases. And if the current flows from outside, right? If the current flows outside, it means you're extracting charge from the capacitor, it is discharging, right? With this convention established, what we told was that, okay, initially the capacitor COS is 2, right, across the device is 2. It was charged to VDC, right? Initially the COSS2 was charged to VDC, right? It is charged to VDC. Now it has to discharge, right? You have to take away charge. You have to take away charge from COSS2. And that is when we told that it would be flowing through the channel itself. COSS2 would discharge through the channel, right? COSS2 would discharge through the channel. And as COSS2 discharges, right, COSS1 will charge up, right? Because the total voltage is VDC. If voltage across S2 is falling, voltage across S2 is falling, S1 should rise at the same time so that the voltage of this plus voltage of this is equal to VDC, right? So COSS2 is discharging, automatically COSS1 is charging up. Okay, so how would COSS1 charge up? It would charge up through VDC, COSS1, and then through the channel of S2 and then back, right? That is the dark green color, right? So that is the dark green color, something like this. That is how COSS1 would charge up. And COSS2 would kind of discharge through the channel of S2 itself. Okay. So that is why we have written over here that COSS2 is discharging through the channel of S2, right? And COSS1 is charging through the entire DC bus loop, through the entire DC bus loop. Okay. So what is the channel current of IDS? Now it is the total load current plus reverse recovery, right? It has some reverse recovery as well, plus reverse recovery of the antiparallel diode, right? And then COSS2 discharging and then COSS1 charging. Do you understand this mechanism?
Yes.
Uh, Okay. So COSS2 is discharging through the channel. COSS1 is charging through the entire DC bus. Okay. As COSS2 discharges, COSS1 has to charge. Okay. If COSS2 is falling like this, right, then COSS1 has to increase like this so that the total voltage is VDC. Total voltage is VDC. Okay. COSS2 and this is COSS1. Okay. So the total voltage is VDC. So if COSS2 falls linearly, COSS1 has to increase linearly at the same time. Right? Total voltage is fixed VDC. Right? We saw how the capacitor charging and discharging parts are. And additionally, there is a reverse recovery current that is flowing through S2. Okay. So this contributes to the overshoot that you are seeing over here. Right? You see overshoot due to IRR, reverse recovery, COSS1 charging and COSS2 discharging. Okay, this is the total current that flows through the device. Okay. Okay. So let's assume again there is an assumption that the capacitances are charging and discharging linearly. Okay. Let's assume linear charging and discharging. That means that dy by dt is fixed. Okay. It charges linearly and discharges linearly. dV by dt is constant. So C dV by dt is also constant. Let's assume for simplicity. Okay. C dV by dt is constant. So it is falling linearly, rising linearly, right? So if I have to complete over here, then let's take some other color. Okay. So if I have to complete, VDS is falling linearly. Okay, VDS falls, and VDS falls like this. Okay, so as VDS falls, right? As VDS falls, there will come a moment that VDS has fallen to a very low value, right? VDS has fallen to a very low value that the device goes from saturation to ohmic region. Do you understand? VDS will keep on falling. At some point, VDS will fall to a very low value that it becomes less than VGS minus V threshold. Okay, that is when the device transitions from saturation to linear region or ohmic region. Okay, is this fine? Voltage is falling linearly, and there will be a point at which the device transitions from saturation region to ohmic region because VDS has fallen to a very low value. Okay, fine. Okay, so I hope this is fine, right? So there is one more thing that we need to discuss for voltage fall. Okay, so let me take a new slide and yeah. So mhm. So, Okay, so let's assume that your VDC is 400 volts. Okay, VDC is 400 volts, and at this moment, so at this moment, right? You know that at the end of your current rise interval, your VGS is V Miller. Okay, so VGS is V Miller at this hint point. Okay, at this point, VGS is V Miller. In our case, the V Miller was 9.5 volts. V Miller is 9.5 volts. Okay, so VGS is 9.5 volts, right? So right now it is 9.5 volts. And over here, right, the drain source voltage was, let's say this is the reference, okay? Okay, so drain source voltage was 400 volts. Okay, and then what happened was we told that the voltage is falling, right? Voltage is falling. Okay, so now you tell me, just see those average voltages, right? Just see this voltage and see this voltage. So what dVdt would be higher? Uh, Compare dVGS by dt and dVDS by dt. Which should be higher? Just tell me. Just make a comparison and tell me. For same dt, what would be higher? dVGS by dt or dVDS by dt? dVDS by dt would be much higher than dVGS by dt. This is very practical. Okay. Now, gate and source are, the difference between gate source is very small compared to difference between drain and source, right? VDS is much higher than VGS. Okay. So what I can write is, what I can approximate is, right, your dVDS by dt is almost same as dVDG by dt. Do you agree with this? Because gate and source are like, see, gate 9.5 volts is nothing compared to 400 volts. Okay. So as far as 400 volts is concerned, it sees 0 volts and 9.5 volts is almost same. So it's like gate and source are like nothing. I mean, gate and source are almost like short as far as 400 volts is concerned. You agree, right? Do you agree with this? Your
Yes.
potential between gate to source is only 9.5 volts, which is very small compared to 400 volts, which is too high. So dVDS by dt can almost be written as dVDG by dt, right? Because gate to source is very small. Okay, so gate and source are like the same point for 400 volts. So dVDS by dt is almost dVDG by dt, right? So let's mark the polarity. This is plus, this is minus. Okay. and if this is plus and this is minus, right? So yeah, so you're telling that dVds by dt is positive, right? dVds by dt is positive. If dVds by dt is positive, right? I mean, sorry, dVds by dt is negative. Sorry, because the voltage is falling, dVds by dt is negative, right? Correct? dVds by dt is negative. Okay. So dVds by dt is negative, right? It is falling. So dVdg by dt is also negative. Do you understand? dVdg by dt is also negative. Correct?
Yes, sir.
Okay. Okay. So dVdg by dt is negative. So the voltage at the drain terminal is falling with respect to the gate terminal. That is the meaning of this. Okay. So voltage over here, right? Voltage at the drain is falling. Okay. That means that if you take this as the capacitor, right? You are taking away current from here. We saw, right? This discharging. dV by dt is negative means the capacitor is discharging. Correct? Capacitor is, I don't know where is that slide anyway. Yeah. So the capacitor is discharging. Right? Capacitor is discharging. Only then you would tell that if it is discharging, it means that you're taking away charge. Correct? dV by dt is negative. So you can tell that during, where is it slide one? So during this particular interval, dg by dt is negative. So you're taking away charge from the CGD capacitance. This is your CGD capacitance, right? CGD. Okay. So the voltage across CGD is like this. The current would be flowing like this, right? And we also saw that dVds by dt is almost same as dVdg by dt. Okay, because gate and source are like almost short. dVgs by dt is nothing. dVgs by dt is very less than both of these. Correct? Do you understand this? During this voltage fall, dVgs by dt, gate source voltage is very less compared to dVds by
Yes,
dt
sir.
and
Yes.
dVdg by dt. Correct? So during this particular interval, right, what I can do is I will draw gate source voltage as almost constant. Okay. Major of the dV by dt appears across drain source and drain to gate, not gate to source. Right? So see, you see over here that the gate current is coming like this, right? The gate current comes like this. It sees two paths. One is through this and one is through this. Okay, one is through this and one is through CGD, other through CGS. Now the point is, how will the gate current split? IG would be split into CGS dVGS by dt plus CGD VGD by dt. Is this agreed? This particular equation? Gate current IG is going to get split into some current through CGS and some current through CGD. CGS dVGS by dt plus CGD into dVGD by dt. Now we told that dVGS by dt is very small compared to dVGD by dt because drain source voltage is falling, which is at a very high potential. Okay. Therefore, I can approximate this as Ig is almost equal to fully CGD into dVGD by dt. Do you understand this? So I can tell that my entire current, right? My So I can tell that my entire current, right? My entire current almost flows only through CGD. Okay, it will flow like this and then complete its path. No current will flow through this, or very, very little current will flow through this capacitor. Do you agree with this, Anandi and Selvakumar sir?
Yes,
Yes,
sir.
sir.
Actually, this first equation we have written CGS, CGD, dVd, VGD by dt. No, is it look like yes?
No, this one, right? This one you are telling.
First equation, Ig equal to CGS
IG.
dVGS by dt plus IGS dVGD by dt. No?
Uh,
This
okay,
one.
it is. Okay, okay. My handwriting is not good.
Okay, okay. Sorry. Then okay. No problem.
Actually, I try to write it as C. Okay, you're right, but I actually try to write it as D only. But yeah, you're right. I think you get it. So this would be, yeah. So this is just KCL, right? So IG is CGS dVGS by dt plus CGD dVGD by dt. Just KCL, nodal analysis at this point. And we told that dVGS by dt is much, much lesser than dVGD by dt, right? Because dVGD by dt and dVDS by dt are almost same, right? So therefore, I can write Ig is almost equal to CGD into dVGD by dt. That means that the entire current, right? Entire current flows through CGD. No current will flow through CGS. Okay. No current will flow through CGS. No current is flowing through CGS. Right? If no current flows through CGS, right? No current is flowing through CGS. Therefore, my VGS cannot change. Right? This is my VGS. Right? VGS cannot change. VGS will remain at V Miller throughout this entire interval. Why? No current is flowing through the capacitor, so the capacitor voltage doesn't change. So VGS remains where it is, V Miller. That is why I have drawn V Miller. Gate source voltage is almost constant. Do you agree? Understand this? Why gate source voltage is constant?
Yes, sir.
Okay, right. So what is the gate current during this interval? Gate current is entire gate current flows through CGD. If you assume that voltage falls linearly at a constant rate, gate current is CGD into dVGD by dt. dVGD by dt, let's assume it is constant. So gate current is also constant during this interval. Okay. So gate current is also constant during this interval. It has a value of CGD into dVGD by dt. Okay. So this is called as the voltage fall period, TF. Voltage fall period. That is, voltage is falling from VDC to a very low value, not exactly zero. There will still be some IR drop and all, but it's a very, very low value compared to VDC. Okay. And we assume that this fall is almost linear, right? This is an assumption we make. Of course, the current would look something like this, right? That will be an overshoot, and then, um, sorry, there will be the reverse recovery overshoot, and then it will be something, reverse recovery overshoot. After the reverse recovery ends, there will still be the COSS charging and discharging current. Okay. This is IL plus IRR plus ICOSS1 plus ICOSS2. This is IL plus ICOSS1 plus ICOSS2. Agree, right? IRR will last only for some time, reverse recovery time. After that, it is going to be just COSS1 charging current and COSS2 discharging current. Okay. I hope you get it. Okay, this is your IL.
Sir,
Okay.
in general, after overshoot, we call it as settling time.
Correct.
So why here we are telling it is a voltage fall period or
No. Voltage fall period is the time taken for the drain source voltage to fall from VDC to zero. Okay.
Okay.
So
Okay.
during this period, we are not quantifying what is the overshoot time of the current and all. Because eventually, why am I actually calculating what is TR and TF? Reason is that simple. Reason is that IDS is also non-zero, VDS is also non-zero. I'm going to have losses. I'm interested in minimizing TR. I'm interested in minimizing TF. Why? Because there is overlap between IDS and VDS, overlap between IDS and VDS. I want to quantify, find out what is this loss. I want to find out what is this loss. I want to minimize it somehow. Okay.
Okay.
That is the entire motivation of finding TR and TF.
Okay.
Okay. Okay. So we have seen two intervals. One is current rise. Next, there was voltage fall. We have seen the assumptions as well, right? That is during voltage fall period, your dVds by dt is much higher. dVds by dt is much higher. And so compared to that, like at 400 volts, your gate source voltage is very small. V Miller is 9.5 volts, and your drain source voltage will be in excess of 400 volts or so. So compared to that, gate and source are like at the same potential almost. So in that case, you can tell dVds by dt is almost same as dVdg by dt. That is, gate and source are almost same. Okay. So dVdg by dt, and this is much greater than dVgs by dt. That is why the entire gate current is assumed to flow only through CGD. Right? Entire gate current flows only through CGD. So far, before this interval, right? Before this interval, the gate current was flowing through CGS, right? Always we saw that gate current is flowing through CGS. Gate current is flowing through CGS, right? Always we saw gate current is flowing through CGS. Okay. But now we see that for only during voltage fall period, gate current is flowing through CGD, right? So let us just quantify what is this. Okay. So voltage fall period, right? So during the voltage fall period, entire gate current flows through CGD. So I is C dV by dt, right? So entire gate current flows through CGD, not through CGS. So CGD dVGD by dt. Do you agree with this?
Yes.
IG is CGD
Yes.
into
Yes.
dVGD by dt. So what is CGD is basically CRSS, right? CRSS into what is VGD? Voltage VGD is changing from what to what? So drain to gate voltage, right? So it is changing from VDC to almost zero, right? We assume that gate and source are at almost the same potential. So VGD is changing from VDC to almost zero. Let's assume it is zero, right? Just for computation, it is not exactly zero. There will be IR drop and all. Let's assume it is almost zero compared to VDC. And what is this period? DT is voltage fall period, TF. This is your IG. Oh, Yeah. So CRSS into VDC by TF. This is your IG. Okay. So this is your capacitor equation. What is your resistance based on the gate source network? You see that we saw that the voltage, right, gate source voltage during this entire period remains at V Miller, right, V Miller, because like dVGS by dt is 0, so voltage remains constant, V Miller, right? So let's draw the circuit. It's going to be VCC, RG, and then there is CGS, there is CGD, right? So this is our circuit. So the voltage between gate to source remains at V Miller throughout, right? So the current IG, right? So IG would be what? IG would be basically VCC minus whatever is the gate source voltage. So VCC so VCC minus VGS is V Miller divided by RG, right? This is the constant gate current that we were seeing this period, constant gate current. Okay, constant gate voltage and constant gate current, assuming that voltage fall is linear. Okay, dV by dt is constant. So CGD into dVGD by dt, right? And the gate source voltage is V Miller, therefore VCC minus V Miller by RG. Equate these two. Okay. Right? Equate these two. Therefore, you will get what is TF. TF is going to be CRSS into RG into VDC divided by VCC minus VM. Do you agree with this? Is this understood? Do you understand how this is happening?
Yes, yes.
Yes, sir.
Okay. So we'll just substitute the values and find out. So I forgot the formula. So what was TF? TF is CRSS into
Into
RG
VDC into
into
RG,
VDC divided by
VCC minus.
VCC minus V Miller. Right. So CRSS was I think 19 picofarad. RG is 13 ohms into VDC. I forgot what is VDC. 585 into 585. I think. Please check. Okay. 585 divided by VCC is 20 and VM is 9.5. Right. So this will give you the answer. I forgot what is VDC. VDC is sorry 625 volts.
625 hours.
Yeah. Into 625. So just compute what is TF. 19 into 13 into 625 divided by 14.7 nanoseconds. Check it, okay? 14.7 nanoseconds. This is the voltage fall time. And what is the dV by dt? dV by dt is VDC divided by TF, right? 625 divided by 14.7, right? So 625 divided by 14.7 is 625 volts divided by 14.7 nano. Okay. So 42.52 volts per nanosecond, or people tell it in kilovolts per microsecond. 42.52 kilovolts per microsecond, right? So every nanosecond, the voltage increases by 42 volts. That is the dV by dt, which is very, very high. Okay. Okay, so this is the dV by dt. This is the dF. We saw what is the assumption that entire current, gate current is redirected through CGD. So far, the gate current was flowing through CGS. Now it is going through CGD. Okay, because the VDS voltage is very high, so the dV by dt across drain source is very high. So dVGS by dt is very, very small, can be neglected. That is why your gate voltage was constant, right? Gate voltage is constant, gate current is also constant. Okay, we learned how to find out what is TR, how to find out what is TF using just normal simple C dV by dt is equal to VCC minus whatever is the VGS divided by RG. Very simple equation, right? Very, very simple equations. Just we averaged it out and found out. Okay. During the current rise time, we averaged out I1 and I2. Right. I don't know. It has hanged my computer. Okay. So we found out what is I1 and I2. And we found out the average, and then are you guys there? I don't know. My screen has hanged. I'm not able to do anything. But
Yes, there. So I'm screen is mid. So it's not.
I'm not able to do anything.
But I have another class. So
Oh, okay, fine, fine. I think we are done with the question. So this is it. I just wanted you to calculate what is dV by dt and di by dt. So we calculated what is the rise time for current, right? So from that you can calculate what is di by dt. Di by dt is basically just a full load current IL divided by dr. That is the di by dt. dV by dt is done. So this question is done. Okay, so yeah, that's what I wanted to tell with you guys. We have been doing this question from last class, but anyway, thanks for hanging around. Any doubts, or can we end the session?
no, sir.
Clear? Whatever
Yes, clear.
was taught in the session. Yeah, so I will upload the slides as well, so you can go through it from the slides also. Okay.
Yeah, sure.
Okay.
Thank you, sir.
Thanks for hanging around, both of you, and have a great week ahead. Good night.
Good night, sir. Thank you.
Thank you, sir.